So, all right, thanks. Well, let's see. So, today, you know, we're used to having 20th century speakers. All of us are 20th century people. Today, for the first time, we have a real 21st century Goddard employee to speak to us. She is Jody Davis, who is an aerospace engineer. She's in the Payload Systems Engineer for the Roman Space Telescope program. Jody got her bachelor's in aerospace engineering from Embry-Riddle, her master's in mechanical and aerospace engineering from the University of Virginia. There, she went on to Langley, where she worked on Cassini-Huygens on the Mars Femur and the Mars Science Laboratory, specializing in the entry, descent, and landing flight dynamics and trajectory simulation for the Curiosity rover. As you recall, this is another one of those 7 minutes of terror experiments where the rover was landed. Well, she's going to tell you about that. Anyway, the Curiosity rover just celebrated its 10th anniversary. It's a very successful experiment. So Jody joined Goddard in 2017, working on the Webb telescope. I won't try to describe the engineering tasks she was working on, but she focused on systems engineering and flight hardware integration and testing. Then she moved on to the Roman Space Telescope. Now, 21st century Goddard employees are not like us. We're not desk jockeys. Jody is very active. She's a Minnesota gal. She's got her pilot's license when she was 18. She likes hiking, travel, running marathons. She's traveled to Tanzania and climbed Mount Kilimanjaro. So this is the new Goddard. So with that, Jody is going to talk about the Roman Space Telescope, personal experiences, and engineering challenges.
Get away from the feedback here. Are we okay, Jen? Sounds like there's a little bit of feedback. Maybe I'll turn down the volume. Does that bother you guys? Can you hear it? The feedback at all? Yeah? Okay. Wow, so thanks, Arlen. That sounded good on paper. I actually like to hear that on paper. But so, like Arlen was saying, I've been at Goddard since 2017 in a full-time capacity, but prior to that, I was at NASA Langley. So today I am going to focus on talking about the things that I've done at Goddard. And really, so the journey that I've had, Arlen talked about it a little bit, worked on the Cassini-Huygens probe, and that was a joint effort between NASA and ESA, the European Space Agency. And then when we landed Huygens successfully, I was addicted to missions. So from there, I worked Mars Phoenix, Mars Science Laboratory. I actually will not talk much about that. We'll save Mars for another time. Maybe I can come back and talk to you about Curiosity and Perseverance. All very exciting. Hard to believe that was 10 years ago, but that was sort of my previous life, working entry, descent, and landing, flight mechanics simulation. An insane modeling of F equals ma. But I'll actually talk about today, we'll focus on Webb and Roman Space Telescope. So on Webb, my role on Webb was integration and test and systems engineering. So I kind of had 1 foot in the systems engineering door and then 1 foot in the integration and test door. And when we get to talk about Webb on the next chart, I worked on the harness radiator and actually installed that to the back of the telescope. So this is about engineering challenges as well. And anytime you're assembling something, especially of that magnitude, there's a lot of engineering challenges with that. Then on Roman, and I actually should have given Arlen an updated bio. So for Roman, I'm the Observatory Interface Lead Systems Engineer. So everything that the observatory interfaces with internally and externally to the launch vehicle, think technical interfaces, thermal, optical, mechanical, contamination, all of those interfaces I have to manage, so there's a lot of engineering challenge with that. And I'll give you a couple examples through that. So we'll talk about the challenges, kind of what I learned, and then we'll deviate a little bit and talk about Roman and what is Roman, because not as many people know about Roman like they do web, and there's some exciting stuff that we're doing. So jumping in, starting with web. On web, so in the corner in the top right there's a picture of myself and my co-lead, Patrick Williams. We installed the harness radiator. What's the harness radiator? So the harness radiator is on the back of the telescope where you can see in this picture here of Webb, it's pointing to the instruments. So the harness radiator's sole responsibility is to radiate the heat from the warm electronics compartment before it gets to the very cold science instruments. And I'm sure some of you are well aware, it might have worked. On Webb, MIRI loves a balmy 7 Kelvin. Right, and so with the MIRI instrument, the mid-infrared instrument, we actually had a cryo cooler on board, and that actually is active and cools MIRI to those temperatures, to those operating temperatures. So with the harness radiator, it is basically just titanium and aluminum slats, and the harnesses are attached to those slats with a Z307 coated shield. And it is out exposed to space, and it just radiates the heat, like I mentioned, from the electronics. So you would think, okay, it's not as complex as a science instrument, right? Well, when I came on board to Webb, it was later in the game. I was really at the start of some of the mid-level, higher-level assembly INT, integration and test. And in that picture, my co-lead, Patrick Williams, and I were responsible for installing the harness radiator. So when you think challenges there's a theme with all of this, and it's the challenge of interfaces. So interfaces here, I was responsible for installing, building, verifying those interfaces that I did not define. And there were a lot of lessons learned associated with that. And especially having to do with communication and teamwork. So one theme throughout all of this is, you have technical interfaces, you have technical problems, and a lot of the times, more than not, the majority of the work involves personal things, soft skills as we used to call them, but all the non-technical aspects, collaboration, communication, things like that. So when it came to installing the harness radiator, this is a publicly cleared picture of us installing the harness radiator. I don't have a laser pointer, so I'm going to step over here to the screen. So I'm on this man lift here in the corner, and this is, you probably recognize sort of the back shape. You can see part of one of the hexagonal mirror segments in the corner. So you're on the back of the telescope now. And the electronics compartment down here hasn't fully been installed yet. The instrument, what we call the instrument module that had all the instruments, that has already been installed. The harness radiators coming on right there. So we had to, Patrick and myself, had to organize how the heck are we going to integrate this thing. It was a blind integration. So what do I mean by blind integration? Not my choice, by the way, but it's something that we had to work with. So these technicians, right, are in this man lift, and this guy here, I think this was Nick, he's fantastic. He could not see the fasteners nor the holes that he was supposed to be seating, torquing down. And so what did he have to do? We had to come up with a scheme with borescopes. So in this other picture here, is another technician who's holding a borescope to give Nick his eyes so that he can see, what he's attaching to. And had I been a part of the design of the harness radiator to the backplane of the telescope, we would not have designed it this way. And so I think this is a challenge that we have continually with these missions, is the forward thinking. How can we integrate this? How can we actually make this work? Do I have reach and access? And at that point, when I came on board, we had, gosh, I think there were like 10 total technicians on the team working this operation. During integration and test, you are, for lack of a better word, kind of under the gun, you are holding schedule. You do not want this thing to be delayed. And I'm sure some of you might have heard about web. We experienced a lot of delays. There's a lot of complexity with these missions. So it was so critical to have communication with the team, make sure that the technician understands, hey, this is what I'm expecting of you. Here's the torque value that you're going to be torquing down these bolts to. So it was a delicate dance of making sure that no one was assuming different things. On top of all of that, we had, as you're installing the harness radiator, you have to monitor the loads of the harness radiator onto the backplane of the telescope. So all of this was a large coordination that we had to work as a team to kind of overcome. But then once you overcome that, and granted it was a small aspect, I know you guys have seen this picture. This is what makes it all worth it, right? So the first images, I understand you all on July 12th got to see these images coming down. And I would have to say at Goddard, the last one there is a relatively new image. We were sitting at Goddard, and collectively, as we were seeing these images at the same time that you were, you could hear gasps from people in the room seeing this for the first time. I believe I said, "oh," in a swear word, because I was just so amazed. But this is why we do these things. And so seeing these images from web, having worked on web and installing the harness radiator successfully, an operation that was supposed to take 6 hours, took 6.5 hours, so we're really proud about that. It gives you the motivation to work the next thing. So it kind of, we started with web, moving on to Roman. So Roman, named after Nancy Grace Roman. So Nancy Grace, Dr. Roman, was the mother of Hubble. And she actually didn't get tenure at the university that she wanted to teach at. And so her plan B was to come to NASA. I just think it's absolutely incredible. At that time, a woman could not get tenure. So she went to NASA and ended up becoming the chief astrophysicist, astronomer for NASA, and argued to Congress that you have to fund this thing called Hubble. And it's very inspiring to me, being a female in a technical, still male-dominated career field, that she did that. And honestly, if you were to set foot in our meetings and see what our room looks like when we're talking Roman technical discussions, it is largely 50% women. And if I could show pictures of all these women that are working Roman, I am so very proud. So I hope as we move forward with Roman, we'll be able to showcase that. But I work with some very talented, powerful women. And the theme here with Roman is now on the front side of designing those interfaces, back to the interfaces, designing them, developing them, managing them. I'm finally on the front end of that with the lessons learned of what not to do on web. And incorporating that into Roman. And then again the challenge is teamwork and communication, leading across organizational boundaries. You have technical difficulties. It's been a lot harder than I thought it would be. But being in more of a leadership position, you have to, I like to say sometimes when I get really frustrated, I'm like, oh, well, really I'm herding cats, playing Switzerland sometimes, but it's all very necessary, and you need someone to help enable the team, and that leadership, work comes into play there. So what is Roman? I think probably some of you know a little bit, or maybe had actually worked with Roman, and I know Tony knows a lot about Roman. So I figured we'd start off with a little video, and then I'll go into some detail. All right, let's see if this works.
The universe. For all we have learned about it, we have only just begun to reveal its secrets. What are dark matter and dark energy? How common are planetary arrangements like our own? And how many planets in our galaxy have the potential to harbor life? The Nancy Grace Roman Space Telescope will help answer these fundamental questions. Formerly known as WFIRST, the Roman Space Telescope is similar to Hubble, but with the benefit of 30 years of technological improvement. Each image from its wide-field instrument will have the depth and clarity of Hubble's best, but capture a sky area 100 times larger. The Roman Space Telescope will take the lead in exploring dark energy and dark matter. We only know they exist by their effects on observable matter, yet these two mysterious components make up 95% of the universe. The Roman Space Telescope's powerful 2.4-meter mirror and enormous field of view will also help us in the search for planets beyond our solar system, or exoplanets. It will watch for gravitational microlensing events caused when a planet and its host star pass in front of a background star. Such events are rare, so catching them requires watching large swaths of the sky. To deepen its study of exoplanets, the Roman Space Telescope will house a beyond state-of-the-art coronagraph that will directly image and analyze Neptune-sized planets in orbits slightly larger than Earth's, a dramatic improvement over current capabilities. The Nancy Grace Roman Space Telescope will help us answer many of the biggest cosmic questions. Its wide-field view and coronagraph will complement missions like NASA's James Webb Space Telescope and Transiting Exoplanet Survey Satellite TESS. The Roman Space Telescope will be an indispensable part of space science during the next decade and beyond.
So I like that video because it actually gives a really good kind of quick explanation of the science, but the mission in general. So we're a Class A mission, same as James Webb, so very, very low risk mission. The International Space Station is the same class. And then we're out at L2, so we're out 1.5 million kilometers, actually pretty near Webb. And then we have a 5-year mission life and a 10-year goal. For our mission. And then it's a survey mission. So instead of with Webb, and I know you'll learn more when Dr. Mather comes to give a talk in October, but Roman is different. It's a survey mission. So we slew, and we actually get full sky coverage for our field of regard in 1 year. I think there's something over 633,000 exposures over the lifetime of our mission. So it's actually very different, but it's complementary to Webb. One thing that actually she said in the video that is a little untrue, I actually we like to say it this way. So the field of view that you're looking at in the image here, it's 200 times the infrared field of view of the Hubble Wide Field Camera 3. That's huge. That's huge. So much bang for your buck in terms of science data with one image. So our mission we have a wide field instrument that has a 0.3, almost a 0.3 degree field of view with 18 4K by 4K Mercator detectors. Another thing that's been quite a challenge that we won't talk about in too much detail is the telescope. Essentially the primary mirror and secondary mirror was gifted to us by a 3-letter government agency. It sounds great. That 2.4 Hubble Lake primary mirror has been fantastic. We polished it for ourselves, but it is a lot harder than you think to take something that was given to you for an application that is not like what we're going to be using it for and make it work for us. It has been quite a challenge. The observatory is huge for us, anyway, not really compared to Webb's sun shield, but it's 12 meters, we're over 10,000 kilograms, and it's a 3-axis stabilized monoprop propulsion spacecraft. And then we have a 1.7 meter high gain antenna, and we have very tight thermal control. So this thing that's kind of, it's labeled here, the outer barrel assembly, or the OVA here, provides not only very tight thermal control, because we need this stability, because when you think slewing, right, survey mission, we have very tight stability requirements, so that outer barrel assembly protects us and stabilizes us thermally, as well as protects us from what we call stray light. Basically, stray light is just light that you don't care about, that you don't want hitting your detectors, okay? So another thing that's very interesting that when you talk about stability is our payload vibration isolation system. So that, we have isolation on our spacecraft, but we also have these things that we call ELVIS. ELVIS is the acronym, so we love to come up with fun acronyms, but it's our launch load vibration isolation system, and it's basically these struts that kind of like Webb, you have this instrument carrier where the instruments are attached, and this vibration isolation system, struts are right here. There's 6 of those. Just for size, we included Dr. Nancy Veris-Roman. I think she was only about 5 foot, but it's really interesting to see in terms of reference. So when you look at the observatory, it's contributed by a lot of different organizations, a lot of different groups. The spacecraft that involves the outer barrel assembly and the spacecraft is provided by us, by Goddard. And then the optical telescope assembly is provided by L3 Harris. And the instrument carrier is Goddard, but also involving Northrop Grumman, okay? And then on the instrument carrier, we have our prime instruments, the wide field instrument, and that's a really great partnership between NASA and Ball Aerospace. And then we have what we're calling our tech demo. It's really essentially a tech demo with direct imaging for imagery and spectroscopy of our exoplanets is the chronograph, and that's provided by JPL. So you can already start to see the complexity of the interfaces organizationally, let alone technically, for this mission. So we talked about a web interface challenge that was on the back end. On the front end, when we were designing the telescope, I think I started working, Roman, in 2017. And it was maybe not even the first year that I was there, not permanently here at Goddard, having worked web and these other missions. And our mission systems engineer said, Jody, can you help with shepherding the optomechanical design for the telescope? And I'm like, man. So what that meant is it was working with all of those different entities that I talked about, kind of holding ourselves up into a room, face-to-face meetings, on top of meetings, on top of meetings, with our optical engineers, our mechanical engineers, our thermal engineers, and everyone else in the room to consolidate and converge on a final optical design for the telescope. In constricted space, constricted volumes, you can't put these mirrors wherever you want. There was a lot of design work that needed to happen in a short period of time. So just kind of the complexity, looking at what you see here in the picture, this is actually what we inherited. So this is the primary mirror and some of the support structure and the struts. What you're not seeing is the secondary mirror and the secondary mirror struts in that picture. So you have light. Light comes in. It hits the primary mirror. Never mind these acronyms because there's a lot to learn there. Primary mirror to secondary mirror. And from the secondary mirror, it travels to the relay optics that pass that ray bundle to the wide field instrument. Okay? So then that gets to the wide field instrument. And then when we're talking about coronagraph operations, that light ray bundle is passed to the relay optics for the coronagraph, and then to the coronagraph. Another thing that you'll see here is all of these lines, these kind of dashed dots, all of those interfaces that are defined there is the most simplest way that I can figure out how to show how everything is connected. And it has taken us years to come up with defining those interfaces, what they look like, what talks to what in terms of data. But designing the optical mechanical design of this telescope was about a 1.5 year total effort. And it was with all of the groups that you see here. Everything is kind of colored. You've got Goddard and you've got Ball and you've got L3 Harris. And so like I mentioned before, the communication, the teamwork, and then now the leadership has the soft skills or those non-technical skills were so much more important than the technical work. And shepherding the design of the optomechanical design for our telescope, I'll say many different personalities in the room and getting people to talk to each other. Communication was key because you have to make sure that someone isn't assuming something different than you that could actually, and it did burn us, and I won't talk about that, but a wrong assumption costs our project managers a lot of money. And so those lessons learned, communication, the teamwork, making sure people are talking to each other, and then the leadership aspect. Someone has to kind of tie all this together and keep the team moving forward. So I actually been quite surprised how a lot of those technical interfaces really just involves the people aspect and making sure that we're a well-oiled machine. The other example I'll give, and this is actually what's ongoing, see those things are kind of blinking green there, those are all of our electrical interfaces and especially all of our harnessing. So I have never seen harnessing on this project, even compared to some areas of web, more complex on Roman than anything else I've ever seen. And what's happening is you have our payload assembly that sits on top of the spacecraft bus, all of that harnessing that provides the communication, that provides the data transfer between our instruments and the spacecraft to communicate back to Earth. It's like, it still boggles my mind to look at it and how complex it is. Unfortunately, I couldn't show a picture because we can't clear that for public, but you'll just have to take my word for it that has been, and it is an ongoing effort, very complex, and in many cases, I was telling Tony this, conflicting constraints. So thermal constraints are this, and then those thermal constraints actually kind of counteract what electrical needs. And so how do you balance that out to come up with an optimal design of how to route all of that intricate harness throughout the observatory? So we've been working through that, and guess what? Face-to-face time is super important. We've learned that communication. Those are kind of, again, those soft skills that are really important. So when it comes to it, I mentioned leaderships. These are kind of my top 3 lessons learned so far that you can apply to anything. And it doesn't even have to be a technical mission at work. It could just be even communicating with my spouse. It's the leadership. If you have good leadership and you're willing to kind of catch the hardship from above, right? So working with project management and making sure that the engineers can have the resources and the freedom and the accountability to do their work, that's important because it enables progress. The other thing, consistent communication. I would get a little nervous sometimes when we hadn't heard from some of the designers at L3 Harris, and so I'd pick up the phone and I'd call them. Well, lo and behold, pick up the phone, see what they're working to, and they were working to a different assumption. So communication and that constant communication is key, and the same things with our technicians installing the harness radio on JWST, on web. It's kind of clear across the board no matter where you're at. You can't do it without teamwork. When I helped support the landing for the Curiosity rover, and then watching the launch for James Webb, both of those times, and I have to say that the Curiosity landing was incredible. I was out at JPL, we were all screaming in the control room. But at that instant, when you realize that this mission had a successful launch, a successful landing, you get science images, you really take a step back and you realize, and you're like, wow, I could not launch a space telescope by myself. I could not land a rover by myself. It is all the team. And that teamwork and that team aspect is something that I'm kind of addicted to. In this picture, you'll see our primary mirror, and then there's a subset of our team. I'm kind of in the center there. And we are starting our lower level assembly. We have a lot of our lower level components for the various elements are starting to come together. Things are really starting to happen. At Goddard, I believe it was earlier last year, our solar panels and engineering unit went in TVAC for testing. Our high gain antenna engineering unit went in for testing. Our flight primary mirror, I love this shot with the American flag, that's been polished, and the optical telescope is working through lower level assembly. And our solar array panels are our solar panels, I took that picture last week on Friday. So hardware is starting to come into the clean room, and we have all of our detectors for the wide field instrument, and we're starting to go through qualification testing for our mosaic assembly. So there's a lot going on, and all those lessons learned, I'm going to continue to work them in with Roman as we start integration and test, just like we did on web. So things are exciting, and if you want to follow along, I'm sure you guys have probably looked at the Roman website, but we continue to give updates, and Twitter, if y'all have Twitter, that's actually a really good way to see what's going on with Roman. But I appreciate the time today, and appreciate you guys listening, and let me know if you have questions.
Question.
Yeah.
Having one Roman telescope, what do you use as a reference? You just hit Star Tracker, or you have any special, like HST, items? I don't know if the coordinate accuracy is critical as it was on HST, but what do you generally use as a telescope?
Okay, I caught the last part of that. What are we generally using to point the telescope? Yeah, so we have our attitude control system, we have star trackers and an IRU. For the stability and slewing reaction wheels, we actually did a trade early on. I was not involved with that, but I can put you in touch with our spacecraft systems engineer. They did a trade study, and there's 6 reaction wheels kind of in a pyramid-like configuration. Our spacecraft has to work to 12 milliarc seconds of jitter, a requirement that is pretty strenuous. So I don't know if that starts to answer your question, but I can definitely get you more information on that. Yes, definitely station keeping. And then, like I mentioned, we're a 5-year mission, but we have a 10-year mission goal, so carrying enough propellant for that. Okay.
Let's see, Hubble and your donor spacecraft are
Yes.
working lower orbit. What's the difference performing L2 versus lower orbit?
Arlen, that is, so I'm not sure if you all heard Arlen's question, but allegedly the telescope that was donated to us was an Earth orbiting telescope, a very different application than being out at L2. The thermal requirements on us at L2, and especially given the survey kind of capability and the requirements that wide field has, on our telescope we've had to make so many changes. That's actually been one struggle for us, is essentially, you have this repurposed hardware, but the majority of the hardware we had to develop, and it is new, so that we can meet our thermal requirements, we can meet our stability requirements. And it's been difficult to kind of couch that to the public and management, where people think it's easy, oh, well, here you go, and it's really not pull out of the box and use. But quite a bit, it's very interesting that you bring up that point, because Earth orbiting is very different than L2, and I know JWST can understand. But Jan, I think.
Yeah, did you say anything about a planned launch date?
Say again?
A launch date?
Yes, fall of 2026. We have our launch vehicle. We're launching on a Falcon Heavy, so that actually was announced, I think, 2 weeks ago. So, which is great, because you hold a lot of uncertainty with your launch loads when you're trying to envelope many different launch vehicles. And so now this is great, so we get to work with SpaceX on that.
Why did you mention that the wiring was proprietary? I thought this would be something you wanted to do. Why is that part of it?
So it's not necessarily proprietary, but Jan asked, why couldn't I show the harness routing? To get some of these images cleared has been difficult. Everything that we have to send is encrypted. Now, if I show pictures of our modeling, I'm hoping we can get a presentation cleared, and I'm not going to offer this up yet to Arlen, but we've done a lot of advancements in our CAD tool that we use is called Creo, on modeling harnesses. And I'm sure maybe some of you know that have worked with harnessing, it doesn't behave how you want when you try to route it. So try to model it is even harder. And we're trying to put together a paper on that and be able to clear some of those images so I can share them with you. But in the interest of time, I just couldn't get them cleared in time. There was another question.
It's an infrared telescope. It's an infrared telescope. What's the operating temperature of these rooms?
So the operating temperature, coronagraph is essentially room temperature. Wide field is 95 Kelvin, the detector assembly. So there's a little disparity in the difference of those temperatures that they need to be held at. And then the optics on, that we kind of talked about, the relay optics and things kind of range from room temperature to 220 Kelvin. So that kind of gives you an idea of the range.
One more question, I see.
Yes.
My name is Michael McDonald. I first came to Goddard in 1962. And in 1966, I went to headquarters. And from 66 to 81, I shared an office suite with Nancy Grace Roman. Dr.
Oh
Roman.
my gosh.
And so
They're still alive.
I think that, or I know that she would be proud of what you and the team of Roman are doing.
That makes me
So
want to cry.
I thought I would mention that.
That's amazing. I can't wait to tell our deputy mission systems engineer and I, we both get very emotional and I can't wait to tell her that. And sorry, what was he? He was Michael McDonald. Okay, thank you.
Any other questions? Well, let's start.
You had a question? Can I still ask you? Let's see, you compared Roman to Hubble with regard to some of the performance, but how do you compare to Webb with regard to, well, for example, wide field camera. Webb has one of those, and for what can show the field of view for compared to Hubble, but what about to Webb? The field of view, the spectral range, spectral resolution, so all of those things. Is there a way of finding out? Can you have a summary of how that's important?
Ernie? So that's a really good question. And for anyone that's interested, Ernie asked about, we compare Roman a lot to Hubble. What about Roman to Webb? We've started to do that a little bit. I don't quite know the reason why we haven't put more out there comparing to Webb. To me, they're very, and I'm not neither an optical engineer nor am I a scientist, but there's quite a few differences in Webb and Roman. More of the point and stare is JWST, the survey mission is Roman. Both infrared telescopes, kind of similar spectral ranges, but I think now they're going to start doing more comparisons. There is a field of view comparison that's out there on the Roman website. We just hadn't focused on it with the public. It's been easier in terms of size and the size of the primary mirror to compare to Hubble. But Ernie, you make a good point, and I want to talk with our public affairs person because I think now, especially since Webb is successful, it would be fun to generate more comparisons between Roman and Webb, especially since they're complementary in many ways. So that's not a bad idea.
Also, much improved coronagraph.
Well, does
Yes. Yeah.
Webb have a coronagraph?
Pardon me?
Does Webb have a coronagraph?
Yes, but this one's going to be a lot more.
Yeah, and Tony's mentioning, the tech demo that we have for the coronagraph, to be able to find an exoplanet of choice, something Venus-sized, let's say, that's interesting to us, use the direct imagery capability that the coronagraph has, suppress the light of this exoplanet, so then you can take a picture of the exoplanet, and then if that's not cool enough, You have spectroscopy on board, so you can show the signature and see, is there methane? I have no idea. That, to me, is incredible public interest, that if the chronograph is successful, that's just the start of it, I think, and a huge improvement from web.
I promise we'd get you out of here in order to go to your meeting.
Oh, thank you.
Thank you very much.